the potash from the ground. The mine will extract material from the prairie evaporate, which is 1,250 meters below the ground surface, well below the water resource aquifers of the Saskatoon, Sutherland, and Empress groups. Potash will be extracted from the Patience Lake, Belle Plaine, and Esterhazy members. The deposit is accessed via drill holes from the surface. To begin a well, a 30-inch hole is drilled to a depth of 10 meters. Then, a 16-inch conductor casing is installed in the well and cemented into place. Next, a 13 3/4-inch hole is drilled to a depth below the near-surface aquifers, which is approximately 200 meters, and a 9 5/8-inch surface casing is installed and cemented into place. The 8 3/4-inch production well is drilled from the bottom of the surface casing to the bottom of the Esterhazy member. A 7-inch production casing is installed to the bottom of the hole and cemented in place. To ensure the entire void between the edge of the hole and the casing is filled with cement, 20% more cement than is required to fill the void is pumped into the hole. Once the cement has cured, a hole will be drilled through the cement at the bottom of the production hole, down to a depth of 10 meters into the halite member below the Esterhazy member. A 2 7/8-inch tubular is installed to the bottom of the hole. Each solution mining cavern is developed using 2 wells. The first step is to develop a sump at the bottom of each well. For cavern development, fresh water is used as a solvent to dissolve the salt. The water is injected and dissolves the halite, creating a brine. The brine is returned to surface where it is disposed of by deep well injection. A blanketing fluid is added to the sump. The blanketing fluid will float on the top of the brine and prevent the solvent from moving up into the Esterhazy member. The roof of the cavern is developed as the sump grows horizontally. The objective of this process is to connect the 2 sumps together. Once the sumps are connected, mining of the Esterhazy member can begin. To begin mining, the casing is perforated to the desired width of the first mining cut, which is typically 1 to 1.5 meters. For primary mining, the solvent is switched to hot water. The hot water flows through the perforations in the casing and dissolves the potash-bearing ore. The saturated brine is extracted from the second well. The blanket material is continually added to the cavern to ensure mining proceeds horizontally along the width of the cut. As mining proceeds, the insoluble materials, such as clays and some undissolved sodium chloride, fall to the bottom of the sump. Unlike a conventional underground potash mine, none of the insoluble materials and a reduced amount of salt is brought to surface per ton of potash mined. The result is no surface storage of the fine insolubles material and a smaller storage requirement on surface for salt. Mining is continued until the Esterhazy member is mined out. Next, a plug is inserted into each well at the bottom of the Belle Plaine member. The caverns are pressurized by preventing flow out of the wells. The pressurization causes a separation between the bottom of the Belle Plaine member and the halite member below the Belle Plaine member. Solvent can then flow between the 2 wells, and primary mining is commenced in the Belle Plaine member. Partway through mining the Belle Plaine member, the cavern will again be pressurized. This will cause the Patience Lake member, the halite member under the Patience Lake, and any remaining Belle Plaine member to collapse, forming rubble in the bottom of the cavern. At this point, the solvent is switched to a brine that is fully saturated in salt and partially saturated in potash. This solvent will only dissolve potash or potassium chloride, and not salt, or sodium chloride, which reduces the amount of salt that will be stored above ground. This process is known as secondary mining. Once secondary mining is complete, the cavern is left full of brine to help minimize subsidence. Directional drilling techniques are used on the production wells to allow for multiple wells to be drilled from the same pad, which minimizes surface disturbance. Up to 40 wells will be drilled from each well pad. An 80-meter pillar is left between each of the mining caverns. This results in a relatively low extraction ratio. 54% of the potash beds remain. The pillars are sized to ensure cavern stability and to minimize subsidence. Subsidence is the localized lowering of the land surface as a result of developing underground caverns. Using solution mining techniques to extract a potash deposit will result in substantially less subsidence than if underground conventional mining methods are used. Using an industry-accepted modeling method, the proposed cavern layout is predicted to result in an ultimate subsidence of 6.7 meters. The subsidence will occur gradually over a large area and will occur gradually over time, taking up to 100 years to reach the ultimate subsidence. On the local scale, the ultimate subsidence is predicted to result in a change of 0.2 inches across 3.3 feet. Therefore, the maximum slope of the subsidence is expected to be 0.22 degrees. This will not be observable to the naked eye. The wellfield is connected to the plant site via a series of 6 pipelines ranging from 20 inches to 30 inches in diameter. The pipelines will be buried 8 feet below the ground surface. The brine is processed using evaporation and crystallization. During the evaporation process, water is evaporated off, collected, and returned to the primary mining caverns. Recycling the hot water results in lower natural gas consumption and a 30% reduction in water consumption. During operation, the process will be optimized to limit the amount of water required. Dust from the process is recovered, and the air is treated in baghouses before being released through the stacks. Air from the dryers is treated in dust cyclones and wet scrubbers before being released through the stacks. Emissions are tested annually to ensure compliance with regulations. Conveyors between the buildings are enclosed in galleries to ensure no dust is released. The site runoff collection pond gathers the rain that falls on the site and other surface drainage. The water from this pond is then used in the process, reducing the amount of water that has to be supplied to site. The salt brought to surface in the brine and separated from the potash in processing is stored on surface. Engineered environmental features are required to isolate the salt storage from the surrounding environment. Underneath the salt storage area, at a depth of 8 to 11 meters, are the clayey tills of the Saskatoon group. These clayey tills are the main geological units that will limit the vertical movement of brine from the storage area. As the containment does not rely on a plastic or geotextile liner, which would have limited lifespans, the system is referred to as natural containment. The starter dike encompasses the salt, and the containment dike collects the brine, which is then sent to the brine reclaim pond for reuse in the process. A soil cutoff wall will be constructed around the storage area. During Stage 1, the cutoff wall will be constructed around the north and east perimeters of the storage area, and during Stage 2, around the west and south perimeters. The cutoff wall is designed to intercept the horizontal migration of brine from the storage area. The cutoff wall is constructed by excavating a 1 meter wide trench down to 1 meter below the top of the clay-bearing tills of the Saskatoon group. The material excavated from the trench is mixed with sand and bentonite and is then placed back into the trench. This creates a barrier of low permeability around the storage area, stopping the flow of brine. Recovery wells will be located around the storage area. The recovery wells will collect brine, stopping it from leaving the salt pile management area. This brine is pumped back to the storage area where it can be controlled and managed. The Stage 1 area is designed for the first 20 years of operation. After 20 years, the salt pile will be 24 meters high. The Stage 2 area is designed for a 65-year life and will have a salt pile height of 40 meters. Excess brine will be disposed of through a series of disposal wells. The wells will be drilled to the Deadwood and Winnipeg formations located 1,800 meters below ground. Like the production wells, the casing for the injection wells will be cemented into place. The space between the tubing and the casing is filled with an inhibitor fluid. Having the void filled by the fluid gives a continuous indication of the integrity of the disposal well. A tubing is inserted down into the deadwood and the waste brine is injected through the tubing. Two diversion ditches around the perimeter of the plant site will divert the regional surface runoff around the site. This system diverts clean water away from the site, reducing the amount of water that could potentially become contaminated, and maintains the downstream water flows. The ditches are designed to handle a 300 mm in 24-hour storm precipitation event. They have the capacity to handle extreme rainfall events. The mine will have an environmental protection plan, and a large component of this plan will be an environmental monitoring program. Monitoring will be required for air quality, ground and surface water flow and chemistry, soil erosion, soil quality, vegetation, and wildlife community. There will be an on-site laboratory for quick turnaround of samples, while other samples will be collected by a third party and sent away to off-site laboratories for testing. Yancoal Canada is committed to building an environmentally friendly potash mine in a sustainable manner and aims to achieve a win-win goal through establishing and maintaining a harmonious relationship with local communities.